Now that we've got the hang of Rolle's theorem, let's introduce a slightly more general concept, one that can actually be proved using Rolle's theorem. Okay. Recall that the average velocity is what we use to initially approximate the derivative. It's just the slope of the secant line between 2 points, right? It's the value, f of b minus f of a all over b minus a. Okay, so for example, let's draw 2 examples real quick. If we have a curve from, on a to b, the closed interval, and maybe the function starts here, and whatever it does, maybe it winds up going to here or so. The average value is the slope of this line. Right? The rise, f of b minus f of a, over the run, b minus a. Okay? Here's another example, same sort of thing, but maybe we're going down, right? Maybe we have a negative slope. Like that. Again, the secant line is the slope of that line. Okay. What the mean value theorem says, more generally, is that if we have a function that's continuous on the closed interval a to b, differentiable on the open interval a to b, then there's some c in a to b and ab such that f prime of c equals f of b minus f of a all over b minus a. So if we just, maybe we continue these illustrations that I had before, we had roughly, okay, so like a and b, and we had a function that did something like that, right? That's what the graph looks like roughly. Maybe I'll try to be a little more slopey about that, okay? Okay. That's the secant line, right? Well, sure enough, there's some point C, I don't know, maybe it's like here or so, where the tangent line is parallel to the secant line. Okay? It's always the case. Note that we're not requiring that f of b equal f of a, but maybe you can see that if f of b does equal f of a, then, well, it's just going to be 0, right? Then you've got Rolle's theorem. Okay? So here's a sort of a classic little example of the mean value theorem. Driver passes mile marker 100 on a road, right? So they're driving at mile marker 100. 2 hours later, they pass the mile marker 260. Right? So I guess they've driven 160 miles altogether in 2 hours. Well, if the speed limit's 65 miles an hour, do we know that the driver was speeding, even if we never actually observed their speed at any given point? Well, let's think about this. So we'll say let t, or actually let we'll say let t be the time after driving past mile marker 100. And we're going to let f of t equal miles after marker 100. Okay. So f of 0 equals 100, and f of 2 equals 260, right? So f is clearly continuous and differentiable, right? The position is clearly continuous. They're not teleporting or anything weird like that. And the derivative, right? They always have a speed, right? They never, shifted speeds at a ridiculous rate. They never like flipped a gear and just instantly dropped 20 miles an hour. That's not a thing, right? So f is continuous on the interval from 0 to 2 and differentiable on the open interval from 0 to 2. Okay. By the mean value theorem, there's some c in the open interval from 0 to 2 such that f prime of c equals f of b, which I'm going to say is f of 2, minus f of a, which is 0, all over b minus a, right? So this is going to equal 260 minus 100, all over 2 minus 0, and this winds up being 80 miles per hour. Okay? So at some point during this trip, we don't know where, but at some point, the driver was speeding. Was going 80 at time C. So they were speeding. Also, just to sort of rub it in, the average speed was 80. All right. So maybe they were going slower than 80 at some point, but that means they were going faster than 80 at another point. Or maybe they were going 80 the whole time. Either way, they were speeding at least somewhere, thanks to the mean value theorem. All right, now lastly, we look at a kind of a challenging problem from Stewart. It always tricks students, holds them up a little bit. It's a mean value theorem problem, right? Example 7. Suppose that the derivative of f is between 3 and 5 everywhere. So we have to show that f of 8 minus f of 2 is between 18 and 30. Here we're kind of using the mean value theorem backwards. F is continuous and differentiable everywhere. I just want to write that out just so we know that we can use the mean value theorem. Okay, mean value theorem's in play. In particular, it's differentiable, I suppose we could say, on... we'll just say, we're going to use the interval 8 to 2, or 2 to 8, but I don't want to have to write closed and open. Anyway, okay? So now, let's see. By the mean value theorem, there's some c in the interval from 2 to 8, right? Because I'm looking at that right there. Such that f prime of c equals f of 8 minus f of 2 all over 8 minus 2. Which I suppose is f of 8 minus f of 2 all over 6. But what do we know about f prime of c? We know that f prime of c has to be between 3 and 5. Because we know that's true for any derivative. Well, then that's the same thing as saying that 18 is less than or equal to f of 8 minus f of 2, which is less than or equal to 30, right? Because you just multiply by 5 to all three sides, okay? So that's how you do this. So, there's mean value theorem and some applications.